Maps, along with cross-sections, are one of the most fundamental tools of the exploration geologist. And in this module, we're going to see how subsurface maps are made and used. In Unit 1, we'll look briefly at the ways we gather subsurface information. After all, that is the first step in map making. In Unit 2, we'll consider contour maps and methods, and the various kinds of contoured surfaces and units that are especially important. We'll also look at one of the most widely used subsurface maps, the structural contour map. Finally, in Unit 3, we'll discuss just a few of the many other types of subsurface maps that are particularly useful to both the exploration and production geologists.
In this technological age of ours, science has created incredible tools with which to view our world. Sophisticated microscopes that can see down into the size ranges of atoms, and powerful telescopes that can look at distant worlds similar to our own. The exploration geologist has to see through solid rock, thousands of meters into the subsurface, where still the only direct information is obtained through boreholes into the earth. The job of the geologist is to fix a drilling location that is only able to sample a minute part of the Earth's subsurface, either directly through cuttings and cores, or indirectly through measurement tools that can be lowered down into the borehole. Subsurface techniques use the same parameters as surface geologic methods, but they don't have the benefit of lateral continuity, unlike rocks at the Earth's surface. It's part of the job of the exploration geologist to extrapolate data from boreholes only a few tens of centimeters in diameter over distances that may exceed tens of kilometers. In other words, to create subsurface maps. Of course, exploration geologists undertake these exercises not as ends in themselves, but in the hope that some of the maps will display anomalies, which may point to the presence of undiscovered oil and gas fields. Oil is where you find it, but in known producing provinces, subsurface mapping has proved successful in guiding the drill towards the more promising areas. In describing the subsurface in map form, the petroleum geologist tends to be optimistic, and the act of mapping expresses his perennial confidence that something will turn up. Of course, geologists cannot go down a hole to obtain our subsurface data. More conventional means are used. Nearly all modern holes are drilled with rotary tools, usually using mud as the drilling fluid and cutting carrier. The kinds of well logs we can make through rotary drilling fall into three main categories: wireline logs, drill cuttings logs, and mud logs. Wireline logs are produced by a variety of physical signals, recorded by instruments and electrodes, contained within a fluid-proof metal container called a sonde. The sonde is lowered rapidly to the bottom of the open borehole. It is then slowly raised back to the surface, continuously transmitting measurements up the conductor wires to a logging truck, where they are recorded onto a moving strip of film. There are three main types of wireline logging: electric, nuclear, and acoustic. Electric logging is the cornerstone of wireline logging services. It may actually encompass 8 or more different measurements involving a formation's electrical resistivity and its spontaneous potential, or SP. These electric logs, together with other wireline logs and cutting samples, provide useful information in identifying and correlating lithologies, and in determining porosity, water or petroleum saturation, and in some cases, permeability. The dip angle of inclined strata can be determined by a special variation of electric logging techniques, the dip meter. It's based on the simple principle of nonlinear points, in this case, the logged records of 4 electrodes, defining a plane. Important nuclear logs are the gamma-ray log, which records the natural radioactivity within different rock types, the neutron log, which measures hydrogen-filled porosity, and the formation density log, which is also useful as a porosity logging tool. Acoustic velocity logs record the travel time of sound waves through rocks. These mainly reflect variations in the elastic properties of rocks and their contained fluids, and have proven particularly useful in evaluating formation porosity. Wireline logs can give us important clues to depositional environments, particularly in the case of clastic sequences. For example, they can be used to distinguish between coarsening upward bar sands and fining upward channel sands. As a rule of thumb, wireline data that pertains to lithology are displayed on the left-hand sides of logs, and those related to fluid saturation and rock properties, like porosity, are on the right. Now that we have looked at how we obtain data in the subsurface by means of logs, let's look at what we can do with it back at the surface. We can look at drill cuttings brought up by the returning stream of drilling mud. Samples are collected at the shale shaker or in a setting box, bagged and labeled at regular intervals, and then they're examined microscopically. The percentage of different rock types is systematically recorded for each depth interval, and the results are plotted on a sample log, sometimes called a stratigraphic or strip log. The sample log can help us determine lithologic breaks and define stratigraphic units, but it must be coordinated with wireline log data in order to work out details of facies, thickness, and interfingering relationships between two or more different rock types. In some areas, for instance, where the lithology is homogeneous or repetitious, cuttings may be used mainly to produce logs that record biostratigraphic data, reflecting systematic changes in the microfossil content of the samples. For example, this evolutionary sequence of fusilinids. It's important to remember that there is a lag time between the chipping of samples by the drill and their return to the surface, and this may amount to several hours for deep wells. Sample and fossil logs must always be corrected to reflect the true depth of sampling. Knowing the capacity of the mud pump, the pumping rate and size of the hole, this lag time can be calculated, or it can be measured directly by adding tracers to the mud stream that are easily detected when they come back up. Uncased walls of the hole with less consolidated and fractured lithologies commonly collapse and contaminate drill core cuttings from deeper parts of the well. Consequently, the first appearance of a distinctive lithology or fossil is obviously something new, not the result of caving, and may be particularly important in reconstructing the borehole stratigraphy. However, since cavings may have a larger size and different appearance than the rest of the cuttings, an experienced sample examiner is often able to disregard them. Cores may be cut when specific lithologic or reservoir information is needed. Obviously, a core is preferable to cuttings because it produces a coherent section of rock for detailed examination and testing. However, cores are significantly more expensive to obtain, and a major difficulty for the petroleum geologist is knowing just when to core. Mud logging, as its name implies, involves the continual inspection of the drilling mud. It mainly records such data as the rate of penetration of the drill bit, sample lithology, and, most importantly, shows of oil and gas in both the cuttings and the mud. There are holes today that are still sunk using cable tool drilling methods, although rotary drills are more common. The cable tool consists of a wire rope suspending a cylindrical bit with a chisel-like end. This is lifted and allowed to fall back to the bottom of the hole repeatedly. The resulting rock chips are removed with a baler.
Now, these cuttings are recovered and significant formation fluids are sampled after each baling with the data recorded on what's called a driller's log. Now, since the new hole rapidly fills up with chips, this usually occurs every few meters. So there is no lag time, and the depths recorded are very accurate. In older petroleum provinces, geologists creating subsurface maps can't ignore a driller's logs, since cable tool drilling was the most common method used prior to World War II. The language of 50 to 75-year-old driller's logs is not very geological true, but they're generally reliable when it comes to locating major formation boundaries and lithology changes. And in most cases, shows of water, oil, and gas are precisely recorded as to the depth, the quality, and quantity. Now, most major oil companies maintain complete in-house libraries of subsurface data, but the smaller companies and independent operators today rely heavily on the existence of log libraries in all important centers of exploration. Many of these are commercial log libraries, but some oil-producing states and governments maintain libraries of drillers and wireline logs, production records, and sometimes cutting samples, and cores for public examination. Now, if a log library isn't convenient, or you need a file copy of the logs and scout reports, you can obtain this data commercially on microfiche. And all the essential information from mapping an entire province can be kept on file in your own office.
We must not assume that all of this data came from vertical holes. Obviously, there are situations where it's impossible or not feasible to drill a vertical hole, as when the subsurface reservoir is beneath a lake, river, or in a metropolitan area. In such cases, the drilling rig is set at a more convenient location, and the hole is deviated to reach the reservoir. In the early days of drilling, many wells were quite unintentionally deflected, what we call a crooked hole. Crooked holes are still a concern in regions of structural deformation and steep dips, where a vertical hole tends to deviate in a direction perpendicular to bedding. In offshore provinces, it's usually economical to drill several wells from a common drilling platform, all but one of which will deviate from the vertical. The engineering technology involved in controlled directional drilling is complex and beyond the scope of this module. But the subsurface geologist must be able to use information from such wells to correct for true vertical depths of correlation points, true bed thicknesses, and true map coordinates of points in the subsurface. This information can be obtained by the use of special wireline directional surveys or from data obtained in a dip meter.
Now, if we're careful, logs made from slanted drill holes can be corrected so that every lithologic marker will fall at its true vertical depth and its proper location. Then we'll be able to incorporate that data into vertical cross-sections or structural contour maps. But that's a topic for the next unit. So read the manual and do exercises 1 through 5 at the end. Now that we have seen how subsurface information is obtained and have looked at the different kinds of logs which we get with different drilling methods, let's turn our attention to using this information in the making of subsurface maps.
Groups of logs within a region display distinctive thin sequences, key beds, or similar configurations and kicks on log curves, all of which can be used as correlation points for subsurface maps and cross-sections. Some of these features may be quite local, but the most useful correlation points are those recognized over large parts of a petroleum province. For example, the top of a widespread blanket sandstone formation. A strong effort should be made in recognizing log markers that are both reliable and regionally continuous. In some areas of the Gulf Coast of the United States, marine transgressions were usually abrupt, and vertical changes from sand to shale lithologies are sharp. These boundaries often make excellent regional markers on electric logs and are particularly useful since they lie just above extensive sands with good reservoir potential. Similar abrupt transgressions are found in many oil provinces, as, for example, the Cretaceous clastic sequence of the Western Interior Seaway in the western part of North America. However, in other areas of the Gulf Coast, for example Louisiana, where rapid deposition took place in deltaic environments, the thickness and aerial extent of individual sand bodies is highly variable. In these areas, thin line stringers with characteristic resistivity signatures must be used as correlation markers. They often result from deposition during periodic intervals of quiet, low-energy conditions, and therefore tend to be more widespread than individual sand bodies. A vertical change recorded on a log can be viewed as either a physical boundary separating two distinctive bodies of rock, like this boundary between sand and shale, or it can be viewed as a visible trace of an abstract geologic event, say the change from shallow to deep marine deposition. In either case, the logged points are just a few of a vast number of such points that generate a three-dimensional surface, a lithologic surface, if it separates two different rock types. We can also define time rock surfaces, which separate all rocks younger than a specified age from those that are older. Time rock surfaces are usually not defined by identical log markers, since facies shift laterally in space through time. Log markers usually define a lithologic surface, even though a comparison of cuttings and wireline curves from the same depth does not always satisfactorily account for the cause of the marker. The notable exception is the paleontologic log, which reflects evolutionary changes in fossil assemblages, and by and large defines a time rock surface. In some cases, lithologic breaks can occur almost instantaneously over large areas. A striking example of this occurs when a volcanic eruption leads to the deposition of a bentonite bed. This, too, represents a kind of time rock marker. It's clear that the basis for all correlation work and mapping is the recognition and definition of markers. 3 or more of these marker points can be used to construct a surface, and once 2 surfaces have been described, they can be used as boundaries to define and enclose units. These can be either rock units, such as a formation if enclosed by lithologic surfaces, time rock units, such as stages and series if enclosed by time rock surfaces, or any arbitrary division that we find useful. The unit has always been regarded as the basic concept in traditional stratigraphic usage, and a rigorous international code has been devised to standardize the definition and naming of such units. But the subsurface geologist feels no such compulsion to follow the traditional naming scheme. He's apt to designate mapping surfaces or thickness units by a single letter, a number, some alphanumeric combination, or a paleontological marker. He recognizes that surfaces are a much more fundamental concept, and surfaces can be used to construct a great variety of stratigraphic units, each precisely measured and defined in whatever manner will help him in the search for oil.
But speaking of that, let's suppose we've just drilled a dry hole. We must have gone wrong somewhere. Maybe if in our contouring we had connected up the points differently.
And you see, that's the heart of the matter. Once we've gone through the time-consuming process of gathering subsurface data, we still have to extend this knowledge beyond and below the control wells. We must judge the validity of the data and our certainty in the conclusions that can be drawn on our subsurface maps. Now, continuous lines are drawn on the map when the information appears to be good and confidence in its interpretation is high. We use dashed lines when the data or its interpretation becomes more doubtful, with shorter and shorter dashes as the uncertainty increases. The geologist attempts to show anomalies on maps, but he must also express his confidence that an apparent anomaly is real. Subsurface mapping usually improves as the density of data increases. But remember, it's still only an interpretation.
The most valuable tool of the subsurface geologist is the contour map. A contour line is a locus of points, all of which have, or are inferred to have, the same value. Any subsurface data that can be quantified can be used to draw some kind of contour map. But some of the quantities that are particularly important to a petroleum geologist involve elevations of surfaces, thickness of units bounded by surfaces, porosity or permeability within a unit, concentration gradients of subsurface waters, thermal and pressure gradients, lithofacies ratios within an interval, and production rates. Given an array of boreholes, a major consideration in drawing contour lines is how to arrange them. There are some standard rules when drawing contour lines that should be followed. They should honor the data. The line should be drawn smoothly and as parallel to each other as possible. They must never cross, and they should be close together where gradients are sharp and farther apart where they're gentle. But even within these guidelines, there are many possible choices. Mechanical contouring, which can be programmed into a computer fitted with a mechanical plotter, is one method of constructing contour maps. Contour interval is selected, and contour lines are interpolated with equal spacing and linear slopes between any two control points. This scheme has much to recommend it because it takes the human bias and tedium out of map making. But there are several pitfalls to this method. One shortcoming of this method is that the control wells are drilled in places where someone had expected to find oil. And, as we already know, petroleum accumulations are most commonly found in areas of structural anomaly, in anticlines or adjacent to faults. Consequently, the control points are apt to be in places where the actual contour conditions are nonlinear. This can be partly overcome by using computer programs that instruct the mechanical plotter to contour the trend surface and small features separately. A second pitfall is that mechanical contouring tends to mask small structural features, which might be good prospects, and tends to create unrealistically large ones, as seen here. It illustrates some of the problems of mechanical contouring. Here is a mechanically plotted structural contour map drawn on the top of a reservoir. This type of map portrays the subsurface elevation of a marker horizon. This pattern shows a large north-south trending anticline having two culminations separated by a saddle. But a closer look at the distribution of productive and dry wells shows this structural configuration to be unlikely. In the apparent structural high in the north, oil is being produced at 6,975 feet below sea level. But at the same and higher elevations to the northwest, the reservoir is dry. At an even lower elevation, in the saddle of the structure, two wells are producing gas. Gas is also produced in the southern anticlinal high, but one of the gas wells is at the same elevation as a dry hole. While mechanical contouring methods may in some cases give a useful first approximation of regional structural trends, a geologist's training and fundamental knowledge of a province's structural and depositional environment enables him to apply a realistic bias to the data and correctly interpret the subsurface structure. In this case, he creates a very different mapped pattern, in which the reservoir sand is uniformly south-dipping, but is cut by steep-dipping east-west normal falls. The productive wells are from separate fields, located along different fault blocks. The interpretive contouring on which the structure contour map is based honors all the data and is consistent with the regional geologic model. It also follows another important rule, that the simplest interpretation that fits all the data is usually the best. The great bulk of subsurface mapping is structural contouring. Let's look more closely at what a structural contour map represents. On a structural contour map, the configuration of a marker surface is expressed in terms of its elevation with respect to a horizontal datum surface. This datum is usually sea level. Ordinarily, the elevations on which the contours are drawn are obtained by subtracting from the depth to the marker the surface elevation of the well. This point, in most cases, is not ground level, but level with a rotary table or Kelly bushing on the floor of the rig, since this is the point from which drilling depths and log measurements are recorded. Usually, marker elevations will be negative numbers, that is, below sea level, except for a few petroleum provinces at high altitudes. On the structure contour map, the elevation of the datum is usually shown next to the well, along with information on any faults which intersect the well. A fault with 200 feet of throw at 3,970 feet subsea cuts this well. The total depth of the well is listed at the bottom. Here is a typical structural contour map from an oil field in Oklahoma. The datum is the top of an Ordovician reservoir sand, and the contour interval is 200 feet. It's fairly easy to visualize the structure here. An asymmetric anticline with a steep northeast limb and a gentler southwest flank. Structure contour maps alone are often sufficient to depict the structures in many petroleum provinces. This is particularly true in cratonic settings, where many fields are located on relatively simple, low-relief folds. But most local folds show some faulting, and many traps are defined or limited by faults. Recognition of faults is one of the major problems in subsurface mapping. When situated between borehole control, subsurface faults may be difficult to detect. Usually faults are not adequately revealed by mechanical and computer contouring methods. Here we see a surface that has been contoured by mechanical contouring methods. Both dips and strikes appear erratic in the central part of the area. In such situations, it is often correct to infer the presence of a fault. In this case, contours should be developed independently from the east and west edges of the area, working toward the locality of erratic elevation. When this procedure is followed, the presence of a fault with a throw between 200 and 300 feet is indicated. A vertical fault, as depicted here, appears on structural contour maps as a linear trace which does not shift laterally with depth. Because they are vertical, or nearly so, such faults are rarely intersected by boreholes. However, in such cases, the presence of vertical faults is often revealed through seismic surveying or surface mapping. In contrast, a normal fault with an oblique fault plane will frequently be encountered in drilling and will be recognized by a missing stratigraphic interval. The interval of missing section equals the vertical throw or displacement of the fault. If two wells intersect the same strata, but only one encounters a normal fault, a comparison of their well logs may reveal the missing section. The stratigraphic interval, as seen between A and B, is present in the well log on the left and is missing from the log of the normally faulted hole on the right. When mapping control points for structural contouring, there will be an area where the normal fault causes our datum surface to be absent. This is called a datum gap, or a cutout zone, because in any well drilled in this zone, the surface we are mapping will be cut out by normal faulting. In map view, the datum gap appears as a linear zone on which no contour lines can be drawn. The width of the datum gap is determined by the amount of dip of the fault plane and the vertical displacement or throw of the fault. In this map, the width of this gap can be determined by solving a simple structural three-point problem, since three wells, not in a straight line, have penetrated the fault plane at elevations of 1,900, 1,400, and 1,700 feet. In this case, the faulted control points all lie within the datum gap, but this is not required. These control points are joined by straight lines. The difference in elevation of the fault plane between well 2 and 3 is 300 feet, and since the contour interval is 100 feet, the line connecting them is divided into 3 equal parts. The difference between wells 1 and 2 is 500 feet, and 5 equal spaces are laid off along that line. Connecting these points of equal elevation gives us contour lines on the fault plane, and the contour spacing reveals the amount of dip. When the fault plane contours are sketched on the map, they intersect structural contours of the same value. The loci of these intersections marks the boundary of the datum gap. In the manual, there are some simple nomograms that will enable you to calculate the vertical cutout and will help you draw cutout zones on structural contour maps. Unlike normal faulting, which causes stratigraphic sections to be missing, reverse faulting causes the interval between A and B to be repeated in wells. This is evident if data from an unfaulted well is available for comparison. Looking at electric logs from these two wells, a prominent kick, seen on the log at the left, is repeated twice in the log of a reverse faulted well on the right. Here is a cross-section showing a high-angle reverse fault that contains oil both above and below the fault plane. In this case, we will need two structural contour maps to properly depict our surface. The line of section runs east-west through the center of our maps. One structural contour map emphasizes the area above the fault plane, and the oil-bearing anticline is clearly indicated. The intersection of the upper trace of the fault plane intersection with the datum is shown as a curved line on the map. Contours to the right of this trace are areas lying below the fault plane, in unrepeated section. On this second structural contour map, we see the marker surface below the fault plane. Its intersection with the fault plane produces the curved lower trace. To the right of this trace, the surface is folded into a syncline, and the upturned edge of its faulted flank has accumulated oil. The distance between the lower and upper traces of the fault plane gives us the horizontal displacement of the marker horizon. As in the case of the normal fault, the reverse fault can be accurately located and contoured if 3 or more control wells intersect the fault plane. Here is a structure section of the Painter Reservoir Field in Wyoming. It demonstrates that the situation becomes even more complex in areas of multiple low-angle overthrusts. Structural contours become totally inadequate in describing a marker at the top of the nugget sandstone, except in local areas. Each major thrust slice would require its own contour map, and in such structurally complex areas, cross-sections and block diagrams are usually a better way to depict the area as a whole. Changes in strike and dip, recorded on a dip meter log, may be helpful in confirming the presence of a fault when suitable unfaulted logs are unavailable for comparison. Away from the fault plane, the strata have a uniform dip angle of less than 10 degrees, but bedding steepens gradually to 40 degrees as the fault plane is approached. Below the fault, abrupt changes in both dip angle and orientation occur. The dip changes may result from drag along the fault plane, as in this case, or in the case of growth faulting, from slump or rollover into the fault plane. It may be possible to infer the strike of the fault from such data, as the dips immediately adjacent to the fault intercept are usually perpendicular to the fault strike. Provided the type of fault is known, normal, reverse, or growth, the direction of faulting may be determined. When dips result from fault drag, they point in a direction away from the fault plane in the downthrown block, and towards the fault plane in the upthrown block. In the case of growth faulting, dips in the downthrown block adjacent to the fault intercept point into the fault plane.
There are other logged properties that can be used to detect faults. Shear zones along faults may be detected on mud logs as a result of hydrocarbon saturation, mud gas kicks, or loss of drilling fluids. These zones also may have increased porosity and permeability, which is indicated on acoustic and density logs. Or they may concentrate uranium-bearing minerals that will show up on nuclear logs. And abrupt changes in temperature gradients or even temperature inversions are often found along faults that are still active.
In addition to their effect on logs, the presence of faults in wells may be inferred from fracturing and veining in cores and from slickensides in well cuttings. Here we found some missing section. There must be a normal fault.
Not so fast. You've forgotten all about unconformities. See, the question of whether a gap in the stratigraphic or a paleontologic section is the result of a fault or of a nonconformity comes up often in subsurface mapping. In fact, it's often impossible to answer from only a few wells. Unconformities are structural surfaces. Now, since some are avenues of secondary migration and others act as traps and seals from reservoirs, they hold considerable interest for the subsurface mapper. But disconformities and low-angle unconformities frequently aren't recognizable in well samples or on electric logs. Now, when this occurs, or when the nature of the unconformity is poorly known, the structural maps that are constructed may not accurately reveal the regional structure.
Here we see low-relief folds buried beneath an unconformity that has considerable topographic expression. The strata below the unconformity looks like a good target, and 4 wells are drilled. But purely by chance, the 2 wells on the high parts of the structure happen to encounter lows on the erosion surface, whereas 2 wells that are structurally low are sited on paleotopographic highs. As a result, the strata below the unconformity are mapped as flat-lying. The underlying structure remains hidden, and drilling was abandoned. In some cases, a marker surface itself may be destroyed by erosion along an unconformity, and the true structural configuration will again be distorted. We can still map and contour the elevation of the top of the underlying formation, but this is not the same as that of the original datum. As a result, on a structural contour map, any contours within the area bounded by the truncated datum will not represent the original structure. Dip meter logs may be useful in revealing angular unconformities. This dip meter log from northern Algeria reveals 2 unconformities that are indicated by electric log. The lower unconformity separates beds dipping 20 to 30 degrees from overlying strata dipping only 10 degrees. The upper unconformity is basically a disconformity, and just above it, beds dip very steeply. This occurs only in the youngest post-unconformity strata, which probably slumped into and infilled the hollows on the erosional surface.
Let's take a break and look at the manual.